Hey there, map makers! Welcome to today's explainer, where we're going to explore one of the absolute coolest topics in our Class 10 syllabus, coordinate geometry. Think of this as the ultimate bridge, right? It connects the equations of algebra directly to the visual, physical world of geometry. If you've ever wondered exactly how your phone's GPS pinpoints your location, or how engineers perfectly align massive bridges across rivers, well, you are in the right place. So let's dive right in and master the map.
Here's our roadmap for today. We'll cover 1. The foundation of the map, 2. The distance formula, 3. The section formula, 4. Mapping triangle areas, and 5. We'll check your understanding. Let's go.
All right, Section 1, Foundation of the Map.
Let's lay the groundwork by quickly recalling some essential tools you picked up back in Class 9. Remember, to locate any precise position on a flat plane, we absolutely need a pair of coordinate axes. We use an x-coordinate, which has a fancy formal name, the abscissa. This tells us our horizontal distance from the y-axis. And then we have our y-coordinate, the ordinate, giving us our vertical distance from the x-axis. Put them together, and boom, they give every single point its own unique mathematical fingerprint.
And notice, this isn't just some dry theory hiding in a textbook. Coordinate geometry is a massively powerful algebraic tool for studying the geometry of figures. It's literally the hidden engine powering real-world navigation, seismology, engineering, and, believe it or not, even art. It lets us understand algebra through geometry, and vice versa. It's truly a game changer.
Okay, moving on to Section 2, the distance formula.
Now that we're refreshed, let's build our very first major tool. Imagine a classic textbook scenario. You need to find the distance between town A and town B, but you can't exactly drag a giant measuring tape across the entire countryside, right? Well, we can just plot them as points P and Q on a graph. By drawing horizontal and vertical lines from these points, we magically create a right-angled triangle, PTQ. And the second we see a right-angled triangle, we can invite an old friend to help us out, the Pythagoras theorem.
Let's figure this out together on our mental whiteboard. We've got our 2 points, P with coordinates x1, y1, and Q with coordinates x2, y2. To find the horizontal base of our triangle, we just subtract the x-coordinates, so x2 minus x1. For the vertical height, we subtract the y-coordinates, y2 minus y1. Finally, we plug these straight into the Pythagoras theorem. The square of our hypotenuse, which is the straight line distance we actually want, is equal to the base squared plus the height squared.
And beautifully, because distance is always positive, taking the positive square root gives us the universal distance formula. It's the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. This brilliant equation lets us algebraically find the exact, precise gap between any 2 points on a map, anywhere at all, just by knowing their coordinates. How cool is that?
Let's actually apply this. If we look at the textbook's town problem, where town B is 36 kilometers east and 15 kilometers north of town A at the origin, we just plug those exact numbers in. The square root of 36 squared plus 15 squared gives us the square root of 1296 plus 225. That adds up to 1521, and its square root perfectly calculates the distance as exactly 39 kilometers. Boom! Zero measuring tape required.
Up next is Section 3, the section formula.
So, having learned how to measure the gap between 2 points, a brand new challenge pops up. How do we place something perfectly inside that gap? This perfectly illustrates the difference between our math tools. The distance formula is like a ruler. It measures the total gap. But our new tool, the section formula, is like a highly precise pair of dividers. It allows us to pinpoint the exact coordinates that split a line segment into a specific predetermined internal ratio.
Let's make this real for a second. Suppose a telecom company needs to position a relay tower at a specific point P on a straight line between 2 existing stations A and B. But they need it placed exactly so that its distance from B is twice its distance from A. That means point P must divide line AB internally in a 1:2 ratio. How do the engineers find the exact x and y coordinates for the construction crew?
Well, we use the section formula. Let's call our internal division ratio M1 to M2. By drawing similar triangles on our graph, we can scale the coordinates algebraically. To find the x-coordinate of our sweet spot, we cross-multiply m1 times x2 plus m2 times x1, all divided by the sum of our ratio, m1 plus m2. And the y-coordinate mirrors this exact same beautiful logic perfectly. We're essentially just blending the coordinates based on the weights of the ratio. Let's plug in some real numbers from a textbook example. We want to find the point dividing the line segment between 4, -3 and 8, 5 in a 3:1 ratio. So we carefully set our m1 as 3 and m2 is 1. Following our formula, the x-coordinate becomes 3 times 8 plus 1 times 4 divided by 3 plus 1. That's 28 over 4, which equals 7. Doing the exact same process for y gives us 3. So our target sweet spot is exactly at the coordinates 7, 3. It really feels like mathematical magic, doesn't it?
All right, let's jump into Section 4, Mapping Triangle Areas.
We have completely mastered points and lines. Now, let's level up from straight lines to flat 2D spaces and figure out how to calculate the area enclosed by 3 points. This is an absolute masterpiece of geometric logic. If we have a triangle ABC on our grid, how do we find its area? Notice what happens geometrically. We draw perpendicular lines from our 3 vertices, A, B, and C, straight down to the x-axis. This forms 3 distinct shapes called trapezia, ABQP, APRC, and BQRC. By simply adding the areas of the 2 outer trapezia and subtracting the area of the bottom one, we are left with the exact area of the triangle inside.
Since we already know the area of a trapezium is half the sum of its parallel sides multiplied by the distance between them, we can simplify that entire geometric dance algebraically, and it gives us this incredibly elegant algebraic formula. It's half of a beautiful repeating cyclic pattern, x1 times y2 minus y3, plus x2 times y3 minus y1, and finally plus x3 times y1 minus y2. It perfectly pulls the x and y values of all 3 vertices together into a single number. And remember, since area is physical space, we always take the numerical or absolute value of this expression. It can't be negative.
Now for our final stop, Section 5. Check your understanding. You guys already know how to do this in theory, so let's put on our detective hats and tackle a quick exercise directly from the text to prove our mastery. Here's a really beautiful puzzle for you. If I give you 3 sets of coordinates, how can we use our new tools to prove if they all sit on the exact same straight line? If they do, we call them collinear. Let's test these points. 1, 5, 2, 3, and -2, -11.
The logic we use here is highly structural. We can just deploy our trusty distance formula 3 times. First, we find the distance between point A and point B, then the distance between B and C. Finally, we find the longest stretch, the distance from A all the way to C. The core concept here is this. If the sum of the 2 shorter line segments perfectly equals the longest segment, then those 3 points absolutely must be in a straight line. They are collinear. If they don't add up perfectly, well, they'd form a triangle instead.
So, the absolutely crucial takeaway from today's explainer is that algebra and geometry are not isolated separate subjects. They are fundamentally, beautifully connected. By mastering coordinates, you literally gain the power to turn visual space into solvable equations. Whether you're finding distances, calculating midpoint ratios, or mapping areas, you now have the exact tools you need. The only question left is how are you going to use this Mapmaker's Toolkit to decode the real-world puzzles around you? Keep practicing, stay super curious, and I will see you in the next one.